All right, so the home bias trade model. I used to teach international economics, so let's talk about a trade model. So in order to have a trade model, you need to have at least two countries so they can trade with each other. You need to have two goods. Why do you need to have two goods? Because if you only have one good, if you have cheese, this is the example I was just used. If you have cheese and I have cheese, then what? If I give you cheese, what are you going to give me in return? Cheese? So you need to have at least two goods in order to have trade. And then finally, in this example, we're going to have an endowment economy, which means that there's no production. It's just each country is endowed with a certain amount of one of the goods. All right, so just some notation. So again, we have two goods. We have the home good and the foreign good, and everything that has a star on it is going to refer to things in the with a star on it, it means things in the foreign country. Without a star, it means things in the home country. So the underscript here is referring to the type of good, and then the star means, say in this case, this means consumption of the good produced at home, or not produced, the home good in foreign. All right, and there's actually a mistake on this slide that I thought that I had corrected yesterday when I was looking over these slides, but apparently I didn't. So there should actually be a star here. And then here it's sort of doesn't really matter. I guess we'll put a star just to be consistent. So this is like the endowment of the foreign good in foreign. So I guess since it's in foreign, we give it a star. All right, so how do we read this? Also, I thought I removed this yesterday as well, which is not necessary. But anyway. Okay, so we have this constant elasticity of substitution utility function. It's the same, it's symmetric in the two countries. The only difference is that the prices at home, in home, are potentially different than the prices of the two goods in foreign. All right. And then anything else to say about this? So theta is the elasticity of substitution. As in the other models we looked at in class that had this sort of CES structure, theta represents how closely these two goods are substitutes. So for instance, if theta is close to infinity, it means that the home good and the foreign good are almost the same. So whichever one is cheaper, I'll just basically only consume that one. If theta is close to 1, here we're going to assume that theta is greater than 1. If theta is close to 1, then it means that whatever the prices are, I'm going to consume about the same amount of CH and CF. Okay. So that's it for notation. All right, so let's immediately talk about an important condition called the no-arbitrage condition. So what this says is, let's look at this equation first because it's easier to explain. If you think about the price of the home good at home and the price of the home good in foreign, they're not going to be the same because there's going to be a trade cost. So if you put 1 unit of the home good on a ship, less than 1 unit is going to arrive in foreign. I mean, I say that as though it's obvious, but that's actually it turns out that that's kind of a standard way of modeling trade costs. So it's just you put sometimes they're called iceberg trade costs. The idea is that if you put a certain amount on a ship, some of it melts on the way to the destination, and it's just convenient mathematically, but it's sort of equivalent to thinking of cost of trade as long as it's sort of a percentage of value, percentage of the good, then that's going to work the same way. All right, so just quick. All right, so these so the way you want to think about this is that there's no possibility of arbitrage here. So we're going to take these the people in our model as price takers. So I'm going to assume these prices are fixed, And think about what happens. They're endowed, so people at home are endowed with a certain amount of the home good. All right, if they send it abroad, then they're going to get 1 minus tau. They're going to be able to sell 1 minus tau units of that good in the foreign country. So to be indifferent between selling it at home and selling it in the foreign country, it has to be true that the price of the home good in the foreign country is higher than the price of the home good at home. And how is that difference going to be mediated? Well, it has to be true that sort of the amount of the good that falls off the ship on the way to the foreign country times the price is equal to the price at home. And then in this situation, people will be indifferent between selling the good at home or sending it abroad. They get the same return, whatever they do. The same is true here. So, I mean, you could just take that 1 minus tau and put it on the other side. The idea is that for the foreign good, the price at home has to be higher than the price in foreign, because if foreign sends some of it to home, then some of it falls off the ship on the way. So how much does that price have to differ? Well, it turns out exactly by this amount here to make foreign sellers indifferent between selling the good in foreign or selling it in home. And again, why is that important? Well, it's important if we want to have an equilibrium where there's consumption of both goods in both countries. Okay, and in general, we are going to have this equilibrium because as consumption falls towards zero, the price would have to go to infinity to prevent people from consuming it. With these utility functions, as either CH or CF approaches zero, then this whole thing is going to approach negative infinity. So that's kind of what's behind that. So since the good is sold in both countries, it has to be true that people are indifferent between selling it in either country. Okay, so using these two equations, let's see here. You can actually just divide them, right? So PF divided by PH, and then on this side, divide this side of the equation. PF star divided by PH star, and then we're going to have this 1 minus tau in the denominator twice. So that's why we have 1 minus tau to the power negative 2. Okay. So the ratio of the foreign price to the home price at home, be careful there, the ratio of the price of the foreign good to the price of the home good at home compared to the ratio of the price of the foreign good in foreign to the home good in foreign, of course, it's going to differ by this factor 1 minus tau. Of course, this thing is less than 1, and it's in the denominator, so this is going to be a positive number here, which makes sense because we expect that the price of the foreign good in foreign will be lower than the price of the foreign good at home, right? So we want this number to be positive so that we're multiplying this times something bigger. But anyway, that's just implied by no arbitrage. All right, so if we were to solve that, no arbitrage is sort of a separate point. Now let's just solve the consumer's utility function for optimal consumption. And as you recall, it was, let's just do this for home. All right, and the budget constraint was PFCF plus PHCH has to be less than or equal to, but let's just say equal to price of the home good times the endowment. Okay, so if let's solve this thing. I think the easiest way to do it is probably, let's do it with the Lagrangian because we want to end up with these things, which will make it easier. So the Lagrangian is just, I'll just do this, equals this minus lambda times that. And then we can change this into a minus. Okay, so that's the Lagrangian function now. take the derivative of the Lagrangian with respect to, let's say, CH, and we'll get theta over theta minus 1 times this, what's inside of the parentheses, to the power theta minus 1 minus 1. All right, then inside, theta minus 1 over theta times CH to the power theta minus 1 divided by theta minus 1, which will be negative 1 over theta. Okay, and set that equal to 0. Oops, not quite. Minus lambda times pH. Okay, we could do the same thing for CF. And by the way, notice these are going to cancel. So I'll just use our conclusion here to this power times CF to the power negative 1 over theta minus lambda PF. And this is equal to 0. Equals 0. All right, so now we can actually just put these pH and PF on the other side of the equal sign and then divide one equation by the other. This term's going to cancel out, right? We're just going to end up with CH divided by CF to the negative 1 over theta is equal to pH divided by PF. All right. Now let's take both sides to the power negative theta, and we end up with CH divided by CF is equal to PF. I'm putting it in the numerator so I can change that negative to a positive to the power theta, which is exactly what we have here. We could have done the same thing for 4 and we would have got this expression. All right, here's our no arbitrage condition from the last slide. Well, this isn't the no arbitrage condition, but we're combining it with the no arbitrage condition. So let's write that down actually from the last slide. PF divided by PH, P star F divided by P star H, 1 minus tau to the negative 2. Okay, so we got PF divided by PH is equal to 1 minus tau negative 2 PF star divided by PH star. That's an arbitrage condition. All right, so that's the right way to do this. All right, so let's substitute. Look at here, we have a PF divided by PH, so we can just put this whole thing here into this into the interior of this thing. So we can write CH divided by CF is equal to 1 minus tau to the power negative 2 PF. This is messy. Let's write it a little flatter. 1 minus tau to the power negative 2 times PF PH star star to the power theta. All right. So that's fine. And then for the next step, we can actually substitute PF star divided by PH star to the power theta. We can substitute that out with CH star divided by CF star. So we actually get this expression, and then that theta is going to be multiplied by the negative 2. So we get this thing here. So actually this is just one more substitution. We get this equation. Maybe I should draw another line here. Putting that into here, we get this. Okay, so in the example that we gave, the utility functions are symmetric, but let's also assume that the endowments are symmetric so that they're exactly the same. If the endowments are the same, then we know that there's the only difference between CH and CF star is just the label, right? Whatever the home country decides to do, it's just going to be exactly the same as what the foreign country decides to do, but just relabeling the goods. So the consumption of the home good at home divided by the foreign good at home is going to be the same as the consumption of the foreign good in foreign divided by the home good in foreign. Just through symmetry, everythh about these two countries is exactly the same. So if that's true, then we can actually just replace CH star divided by CF star with CF divided by CH. So then we're going to get CH divided by CF is equal to 1 minus tau, negative 2 theta. And then here, CF divided by CH. Okay? So multiplying both sides by CH divided by CF, we're going to get CH divided by CF squared is equal to 1 minus tau to the power theta, negative theta, squared. All right, take the square root of both sides, and not worrying too much that we have negative values of consumption, since they have to be positive, let's just write out 1 minus tau to the power negative theta. And then that's just another way of writing this expression here. Okay, so that leads to this with just one more small math step. Okay, so what have we done? We've derived relative consumption of the home and foreign good as a function of trade cost. Okay, so all we have to do now is just, we can see if this is reasonable. So do people consume a lot less of the foreign good than they consume of the home good? This is this domestic bias in international trade. Can we explain how much more people consume the home good based on reasonable parameters theta and tau? Okay, so that's the name of the game here. So what we're going to do next is we're going to plug in a couple of potential thetas and taus. Oh, there's one more step. Okay, there's a little bit more algebra here. I was thinking this video is getting a little long. Let me stop here, and then I'll start up on in the next video with this additional step, and then we're going to plug in some parameter values.